short story. The question I've got is, in your modeling, in terms of erosion and depth of the mushy layer, were you able to vary the consolidated nature of what you were eroding and the depth of that consolidation? Was it just sort of a solid layer that you were eroding, or gradationally unconsolidated? And to what sort of depths were you doing that in terms of unconsolidated to consolidated?
We don't have direct, I agree, first of all, that's we bias. We will like black and white rocks. They're so nice. And therefore we go there, because if you have a paraxenite and a mafic, you cannot really see anything. And definitely. In terms of this, what you're saying, do we have this constraint? I don't think we have really good constraints. Because I think we see these sharp boundaries from my point of view up to the trap. And we don't see, you know, I would say like that the process is not put in action. We don't see any kind of intermediate stage which would allow us to say that. Because I look at this Robert data where showing in granites, when the mafic granites is magma percolating, you see this the depth of percolation, you see there was a grades and magma, so you see preparation. But in our case, it just
Okay, thank you. We are going to have to cut the discussion now, I'm afraid. I'm sure there'll be opportunities to discuss in the coffee break. I do notice there's a question in the chat here, but I don't think we can take that at this stage. So apologies for that. Hopefully there can be an answer later on. So our next speaker for today is Tahnee Otto, who will be talking about peritectic crystal entrainment.
Can you just admit Marina, please?
How do I do that? Okay, great, thank you. Okay, over to you.
Thank you. All right, yeah, good morning, everyone. So my name's Tahnee. I'm from Stellenbosch University, and I'm going to talk to you a bit about the work that I did during my PhD. This is actually my first, there we go, better, first talk after graduation, so definitely something to remember. Here in this picture, I've actually now given it away. I say layered mafic intrusions, but this is a photo of some of the chromatites in the Bushveld complex in the upper zone. So now you know where we're starting. So we've had some very interesting talks this past weekend, workshops, and there's really some interesting and excellent work being done in terms of layered intrusions and chromatite formation. So I think, you know, with that being said, starting off, I'd really like to, after this talk, mainly leave you with something to think about and a new idea for like the general formation of layering, and now in particular in the Bushveld complex. But I'm really not trying to sort of give a mode for the chaotic details of how it might have formed. There's a lot of people that are working on these things in detail, but so this is more just sort of a general idea. So now that I've used up enough time on my Bushveld slide, because you all know the Bushveld relatively well, I'm just going to obviously draw your attention that today I'm mainly going to talk about the lower parts of the Rustenburg layered suite, so the lower zone and the critical zone, because this is where we find these massive reserves of chrome in chromatite seams of variable thicknesses. Right, so the Bushveld enigma itself, there's been several magma compositions put forward as parental magma, so if you're Bushveld 1, Bushveld 2, and so on. The thing about this is we already know that chromium has limited solubility in mafic melts, and you know these parental magmas taken from dikes and sills. It's quite obvious if you actually just look at what's in the critical zone that the chrome content is in excess of what these magmas suggested as parental could have held in solution. So let me just look at my little drawing there on the left, just do a little bit of maths. You take a chrome solubility of about 0.12% at 1,300 degrees in FMQ. That's going to tell you that for every 1 meter of chromatite, you need about 790 meters of source liquid. So if we then do a little bit more maths and we take the cumulative thickness proposed, put forward by Eels, then that gives you about 15.9 kilometers of magma that you would need to form the critical zone only. So I gave this talk at the Geo Congress at the beginning of the year. So if you've heard it before, then sorry about that. But actually managed to have a chat with Stephen Privek there, and he told me that actually also did these calculations. So then taken them from his paper, actually, which really works well, did it for these specific magmas. And then you can see that for B1, B2, and even if you considered a contaminated komatiite, you need quite a lot of magma to make up for the chrome content in the critical zone. So we see as a result, you have a whole bunch of models trying to explain this. I think you obviously have your mechanical and your chemical views, but they can generally sort of be put under these umbrellas of either crystal slurries or chrome saturation of the liquid as an explanation. So trying to think about, you know, the parental magmas as a starting point, one of the big questions we're asking ourselves is, well, what is the source? What exactly is melting? How much is it melting? And what do the stoichiometry of these melting reactions look like? So we also know from experimental studies done in the mantle that you do have spaces where melting in the mantle is incongruent. So this particular reaction has been put forward by Kinsler and Gruber and a few other people, where you can then actually see the formation of peritectic orthopyroxene. So you have this phase that grows in abundance as melt grows. Some works that are now more done on granite magmas have also shown that the incorporation of these peritectic assemblages actually exercise an important control on the chemistry of the magmas. So that's taking that into consideration brought us to the next point of, well, what if it wasn't only melt leaving the source, but a magma leaving the source? So in other words, melt and crystals, and what impact would this have on the formation of layering? Just a quick recap on this peritectic crystal formation. If you have your some sort of rock at subsolid conditions, you start to heat it, melting starts to happen, generate your triple junctions. This is also the point at which your peritectic crystals are going to form. So importantly, these crystals are suspended in the melt. And then when you reach a particular melt threshold, then when your melt's extracted, your crystals can be entrained. And importantly, this is going to change the chemistry of the magma that's been extracted. So we investigated this using phase equilibrium modeling. So I used R-Crust software. R-Crust generally uses R and is a front end using the minimum of Perplex. Important thing about R-Crust is it is path dependent. So it allows us to look at bulk compositional change. In other words, what's the residual system that stays behind or the extracted system as we're simulating magma extractions. So those are just some of the details of the modeling and then the composition of the peridotite. I've modeled a few peridotites, but I've just used this one here because it's from Premier in the Western Bushveld, so it seems apt to use that in this particular setting. The thing that's lovely about the thermodynamic modeling is we can take our bulk composition, we can do batch melting exercise over 15 to 30K bar. And from the PT pseudo section that gives us, we can now go, and in this case, plot the abundance of orthopyroxene and spinel across this PT space. So the figure there on the left. What's important to see here is then after you pass your solidus, you get points where you have your phases that increase in abundance. So going from lighter to darker color. This would obviously mean that these are your phases that are increasing with melt. And this would then be considered your areas of peritectic phase formation. So I've added the little area there for spinel, but obviously that's really high temperatures, so not considering that. But if we then continue on past that space, you'll see where your colors start to become darker again. So this is where your peritectic phase is no longer growing in abundance, but now becomes part of the reaction. With the PT pseudo section, you can obviously investigate any particular path that you'd want, isobaric, decompression. In this case, modeled two paths, a low temperature and a high temperature path. So here, if you follow along this high temperature path, in this case, you're obviously starting somewhere up there high before you hit the solidus. The solidus. You start to see melting happening. You have your garnet that's being consumed. You actually see a little bit of peritectic clinopyroxene initially, and olivine is relatively uninvolved. Then you actually get to a point where your garnet is exhausted. peritectic clinopyroxene is also consumed, and at that point you see your peritectic orthopyroxene forming. Very importantly, the peritectic orthopyroxene in this particular case is the first orthopyroxene that you see, and also important is that it has orders of magnitude chrome higher than what melt can actually hold in solution. So once we've identified these points where you see this peritectic orthopyroxene formation, now we actually want to investigate what would happen if you entrained that to the magma and how that would affect the magma chemistry. So this is just an example of where some of these extraction points would happen. So you have these 6 sequential extraction points. This was set that every time your melt reaches a fraction of 5 weight %, you extract the magma and whatever peritectic crystals may have formed along that point. So, in your case, you have your first extraction would mainly have some melt and peritectic clinopyroxene, then melt and orthopyroxene, and thereafter the extractions were stopped. This is just an example. I've put it later in my slide because I didn't really know how my time was going to go, but just note that I've just put these points here as examples, but that's not actually how your system's going to look. Obviously, your residual system will change as you do extractions along those points. So I guess here we now get into our, is it a slurry? Is it a melt saturation? All those things. I don't know, as Rice would say, but in my world, this is going to be a slurry, particularly because of what we see from our results. If we model this at emplacement, which we've actually done here, but I'll get more to that later. If you consider the density as well as a sequence of formation in cumulate formation. So you can see here that you have your chrome spinel. It is a much higher density than your olivine. Olivine, orthopyroxene, clinopyroxene has very similar densities and then form in sequence and together. And then finally you have your pelagic layers, which would be suspended in the melt, having very similar densities. So after you've had all your phases that have separated by gravity, and you then have some sort of filter pressing and compaction, your pelagic layers crystals can stay behind and your melt will migrate off. So now we get to the point of actually modeling our extractions at emplacement. So this was done at about 3K bar, sort of crustal conditions. You can see the interesting thing about if we run the exact same model and we do our sequential extractions with melt only, you take one of these melts and you emplace them, this showing cumulative phase abundance with decreasing temperature. You see a lot less crystals forming, and if you cool down to about 1,000 degrees, you have quite a lot of melt that's still left, but importantly, you also have no chromite. If we do that exact same thing with one of the magmas that were extracted that is entraining peritectic orthopyroxene, firstly, at your high temperature emplacement, you would see that the magma would arrive in the magma chamber already as a crystal slurry. So importantly, you'd see the immediate production of layers, and very importantly, you have your chromatite. And then you see the very sort of similar phases that you're going to find in your ferromagnesian layers and the crystallization sequence. And some from your example cumulates, you can then produce your donites, your peroxenites, and eventually an anorthosite if you were to have your sort of filter pressing towards the end. So if we then go and apply this to our the Bushveld complex and what we see in the low and critical zones, you can actually see that the example cumulate looks very similar to what we see in the lower part of the Bushveld complex. Cooling doesn't always have to go all the way down. It can end at any point and have your melt migration up. So if you have then several of these sort of still emplacements, then you can actually also generally form these layers with your chromatites. Between. So just trying to summarize that. If we look at partial melting in the source, we have our peritectic phase formation. We entrain these peritectic phases to the melt upon extraction. This peritectic phase will equilibrate with the melt during ascent, at which point the melt and orthopyroxene then produces spinel and olivine. This is in place as a crystal, high temperature emplacement as a crystal mush, and with effective density separation, then you can form your layers of chromatites, your donites, continue on to your peroxenites, and eventually some anorthosites. And just very importantly, you obviously have your chromatites there, which is what we're looking for. And because we're bringing the chromium in with the orthopyroxene and not with the melt, you actually end up having a lot less melt. So you then don't have all this excess melt that had to have gone somewhere that we don't see anywhere in the rock record. So yeah, thank you for your time.
Very much. We have time for a quick question up here. Just wait for the microphone, please.
Thanks. What percentage of crystals versus melt do you have in this mush?
Well, it depends on the different mushes. So I'll show a few here. Depending on the extraction, you can have, say, the example, 44% orthopyroxene, or you can have higher percents. It was modeled in two ways. So it was modeled for extractions where you have minimum. So that would be the peritectic crystals that have only been produced in the previous temperature interval, which would be 10 degrees, or you can do it all the crystals that have been produced from the solidus or from the previous extraction. So, yeah.
Okay. Another question down here.
Hi, thank you. I do really like the idea that you can use orthopyroxene to increase your chromium content, but as a sort of fairly regular user of the HP databases and their phases, I was just wondering about whether you've been able to do any tests of your sort of chromium partitioning, because it's when you're mixing models like between the different years, compatibility, I'm sure you're aware compatibility can be an issue, but a really good way to test it is to look at the partitioning in your 3 kilobars. Were you able to have a look at that, and what did it look like?
If you're talking about partitioning at emplacement, because actually I've looked at what the partitioning would be along the melting path at the bottom right. So you can then actually, if you look at your abundance and you compare that to partitioning, it's actually giving partition values for orthopyroxene that are a little bit lower that you would see. So it's actually probably underestimating at that point how much chromium would be there.
Cool. So you've been quite conservative. Yeah. That's it. And is that a slide you prepared earlier?
Sorry, say again?
No, nothing. All right. Thank you.
One more quick one here, if you want.
Okay, I just want to comment on these B1, B2,
Yeah.
whatever. Okay,
we're assuming that B1, B2, etc. are parental, but they actually are cell phases that are extruded out of the bushveld. So you put in magma, and then these cells go outwards from, and you can get rid of a lot of magma that way.
Yeah. Okay. Thank you.
Okay, thank you. We're going to have to move on at this stage. Thank you very much.
Thank you.